So I got this problem where I've got some traffic lights and I want to go from red to red amber to green to amber and background to red. And I want to do this in hardware, so I'm going to have to find some way of representing the lights. I'm going to use bit strings to do that, and uh, I've been given the encoding I should use here, so the most significant bit should represent green, the second least significant bit should be what's that, amber, and then finally red. I'm going to use four, four. We're going to use a nibble or 4 bits to represent our traffic lights. So the first thing we want to do is have a look at the transitions we go through. So initially when we've just got red, then our bit string looks like this. So our top bit is always unset, then this bit here corresponds to green. So is green set? No. Is amber set? No. Is red set? Yes. And then for red amber, it's very similar. You have a look for each bit. Is green set? No. Is amber set? Yes. Is red set? Yes. So our string looks like this. Green. So 0, is green set? Yes. Is amber set? No. Is red set? No. And then we go to amber, and we've got 0 initially. Is green set? No. Amber set? Yep. And red is not set. So now we've got our sequence of numbers, and if I just make this a bit bigger, we then want to find out how to transform one state into the next state, and we also want to loop back around to the start state. And how are we going to do this? I think the first thing to do is have a look at what we have to do to transform from one state to the next state. So here we've got 1 and we want to go to 3, so we add 2. Here we're at 3 and we want to go to 4, so we add 1. And then here we're at 4 and we want to go to 2, so we take 2 off. And then when we're at 2 we want to go back to 1, then we take 1 off. So we need to find some way of generating our transformations, and the only information we have to calculate these transformations is our current state. So if we're in the red state, we've only got this information. And it turns out there's quite a nice trick to this. If we observe the change in states and the sign or the number for let's look at the sign. Okay, so say I want to calculate the sign for this transformation, and I've only got this data. Well, I have absolutely no idea. So what I'm going to do is have a look at where else I want to perform an addition and see what similarities I have between the two states that are different from the other states which don't perform additions. So initially I'm seeing that the first bit is set for both of these states, and for each of these states you want to add to get to the next state. Whereas for the ones where we want to perform a subtraction in our transformation, the least significant bit is not set. So this gives us a way to calculate to calculate whether we want to perform a subtraction or addition for our calculation. And the way we do that is we look at bit 0, and if it's 1, then we want to add. Otherwise, if it's 0, then we want to subtract. So we can use this to select inputs to an arithmetic unit that performs either subtraction or or addition or subtraction. And now we want to have a look at 2 and 1. Like how do we know whether we want to add 2 or take away 2 or add 1 and subtract 1? And we use the same trick again. We have a look to see, let's look at 2's first. What do the states have in common where we're going to use 2 in our transformation? So I mean all of these bits are 0, so let's have a look at which bits are 0 in this transformation. So we've got this first bit, but we've already, the first bit is different to this one here, so that's of no use. This bit here might be of use. Oh, actually, hang on a sec. No, I'm looking at the wrong one. Okay, so this state here and this state here both produce transformations of 2. So they have differing least significant bits, but the next bit along is the same. Now I want to have a look at the other states and see whether their second least significant bits are set, which they are, which allows us to determine whether we want to use 2 or 1 in our computation. So if our bit 1 is set, then let's see, if bit 1 is set, then we want to use 2. No, we want to use 1, sorry. So, we want to use 1, and if it's not set, then we want to use, so here, bit 2 is not set, and we have 2 in our transformation, which you can confirm by looking at this one here, which is calculated from this state up here. So now we've got a way of calculating our transformations based on our current state. So these are bits of our current state. So bits of current state. And now we want to build some hardware that does this. So we need to be able to either add or subtract. And the way we choose between options is with multiplexers. So we're going to have an addition and subtraction. I'm going to have some registers that store the last state and the next state. And we're also going to want to select whether we use a 1 or 2 in our transformation. So by default, when bit 1 isn't set, then we select a 2. Otherwise, we select a 1. And these multiplexers are controlled by certain bits from the last state. So this one here was selected by bit 1, and this one up here was selected by bit 0. So now we've got our diagram, and we can go ahead and implement that in a simulator, which is what I'll show you in the next video.